Pick up a glass of water and set it on your desk. It sits there, perfectly still, the water level flat, the surface undisturbed. Now imagine that glass is the earth, and the water is the ocean, and some unimaginably powerful force, reaches out and stops the glass from spinning. The water does not stop. The water keeps going. It sloshes against the side of the glass, climbs the walls, and spills. That is, in the roughest possible terms, what would happen to Earth's oceans if the planet suddenly stopped rotating. Except the glass, in this case, is 12,700 kilometers in diameter. The water is an ocean with an average depth of 3.7 kilometers, and a spinning is a rotation of the Earth's surface at the equator of roughly 1,670 kilometers per hour, faster than the cruising speed of most commercial aircraft, moving continuously every second of every day of every year. The sloshing that would result would not be a spill. It would be the largest wave in the history of the planet. And that is only the beginning of what would change. If you enjoy videos that take the most seemingly impossible questions in earth science and physics and work them through to their real, precise, often devastating conclusions that never flinch from the numbers, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this topic is that Earth stops rotating means the same thing as nothing moves. People imagine the planet simply pausing, the way a spinning top slows and stops, and assume the main consequences would be something like very long days and very long nights, an inconvenience of timekeeping, a disruption to schedules. This is wrong in a way that needs immediate correction before anything else, because the entire rest of this video depends on understanding one fundamental fact. Stopping is not the same as having stopped. The consequences of Earth's rotation ending depend entirely on how it ends. A planet that has never rotated is a different place from a planet that used to rotate and suddenly doesn't. A planet whose rotation has been slowing imperceptibly for billions of years is a different place from one that stops in an instant. These are not the same scenario, and conflating them leads to conclusions that range from the merely inaccurate to the catastrophically wrong. So we will do something more careful. We will explore not one scenario, but several, arranged by the speed of the stopping, from the physically instantaneous, which is not actually possible, but whose consequences illuminate the physics, to the geologically gradual, which is what the laws of celestial mechanics actually predict. Each scenario produces different consequences, and those consequences reveal different things about the structure of the planet, the behavior of its atmosphere and oceans, the nature of its magnetic field, and the architecture of the life it supports. We will start at the most extreme end, the instantaneous stop, and work our way backward through the less extreme scenarios, because the extreme case clarifies what forces are in play, even when the specific scenario is physically unrealizable. And along the way, we will discover that Earth's rotation is not merely a feature of the planet, it is the foundation on which almost everything about the planet's habitability is built. Begin with the rotation itself, and what it actually means for the surface of the Earth to be moving at 1,670 kilometers per hour. Earth completes one full rotation every 23 hours, 56 minutes, and 4 seconds, a period called the sidereal day, the time it takes the Earth to return to the same orientation relative to the distant stars. The solar day, the 24-hour cycle we divide our lives by, is slightly longer, because the Earth also moves along its orbit around the Sun while it rotates. So it needs to rotate a tiny bit extra to bring the Sun back to the same position in the sky. The rotation speed of a point on Earth's surface depends on its latitude. At the equator, where the circumference of the Earth is largest, a point must travel roughly 40,075 kilometers, the circumference of the Earth at the equator, in 24 hours. That works out to approximately 1,674 kilometers per hour, or about 465 meters per second. At 45 degrees latitude, roughly the latitude of Minneapolis, or Rome, or Wellington, New Zealand, the circumference of the parallel circle is smaller and the rotation speed is approximately 1,180 kilometers per hour. At the poles, the rotation speed is essentially zero. A person standing at the geographic North or South Pole simply spins in place, returning to the same orientation once per day without travelling any significant linear distance. Before we explore what happens when the rotation stops, it is worth dwelling for a moment on what the rotation actually does, not just to the surface of the planet, but to the fluid systems that cover it. Because the Coriolis effect, which is the apparent deflection of moving objects caused by the Earth's rotation, is perhaps the single most consequential physical influence on the large-scale behaviour of the atmosphere and ocean. And understanding it is essential to understanding why its loss matters so profoundly. The Coriolis effect was named after the French engineer Gaspard Gustave de Coriolis, who described its mathematics in 1835. It arises because we're observing the motion of objects from a rotating reference frame, the surface of the rotating Earth. In an inertial frame, a non-rotating frame, there is no Coriolis force. Objects travel in straight lines, unless acted on by real forces. But to an observer on the rotating Earth, objects moving across the surface appear to curve, to the right in the northern hemisphere, to the left in the southern hemisphere. This apparent deflection is the Coriolis effect. Think of it this way. Imagine firing a cannon from the North Pole straight toward the equator. In an inertial frame, the cannonball travels in a straight line south toward the equator. But while the cannonball is in the air, the Earth is rotating beneath it. By the time the cannonball reaches the equator, the target on the equator has moved eastward due to the Earth's rotation, but the cannonball has not. The cannonball, which has no eastward velocity because it was fired from the pole where the surface velocity is zero, arrives at the equator east of where the target now is, or, equivalently, the target has moved east, away from the cannonball. To an observer on the rotating Earth, the cannonball appears to have curved to the right. This is not a real force. No one pushed the cannonball sideways. It is simply the effect of looking at inertial motion from a rotating frame. The magnitude of the Coriolis acceleration is 2 times omega times v times sin latitude, where omega is Earth's rotation rate, v is the speed of the moving object, and latitude is the geographic latitude. At Earth's current rotation rate, the Coriolis acceleration for a parcel of air moving at typical atmospheric wind speeds of about 10 meters per second is roughly 0.01 meters per second squared at 45 degrees latitude. A small but continuously acting deflection that accumulates over the large distances and long timescales of atmospheric motion. Over the hundreds to thousands of kilometers and days that large weather systems persist, this small but continuous deflection organizes the atmospheric flow into the characteristic rotating patterns, the cyclones and anticyclones of the middle latitudes, the Hadley cells of the tropics, the subtropical jet streams that make global weather as organized and predictable as it is, within the chaotic limits that any meteorologists will readily acknowledge. The same Coriolis deflection acts on the ocean. The trade winds, the persistent easterly winds in the tropical Atlantic and Pacific, blowing from northeast to southwest in the northern hemisphere and southeast to northwest in the southern, exert a sustained drag on the ocean surface. This drag, combined with the Coriolis deflection of the wind-driven current, causes the surface water to flow not in the direction the wind is blowing, but at roughly 45 degrees to the right in the northern hemisphere. As you go deeper in the water column, the current direction rotates further to the right and decreases in magnitude, a spiral called the Ekman spiral, named after the Swedish oceanographer Vagner Wolfrid Ekman, who described it mathematically in 1905. The net transport of water due to wind and Coriolis, the Ekman transport, is actually perpendicular to the wind direction at 90 degrees to the right of the wind in the northern hemisphere. This is why the trade winds blowing westward across the tropical Pacific drive a net northward transport of surface water along the eastern boundary of the Pacific, causing cold, deep water to upwell along the coast of Peru to replace the north-moving surface water. This upwelling, driven by the Coriolis effect acting on wind-driven surface currents, is the source of the extraordinary productivity of the Peruvian Anchovy fishery, historically one of the most productive marine ecosystems on Earth, which in turn supports enormous bird populations and human fishing industries. The Coriolis effect, acting on trade winds generated by the Coriolis effect itself, through the atmospheric circulation, creates the upwelling that fertilizes the eastern Pacific with cold, tide over tide, nutrient-rich water, and makes it one of the most biologically productive ocean regions on the planet. Remove the Coriolis effect by stopping the rotation, and the Ekman spiral disappears. The upwelling, driven by Coriolis deflected currents, stops. The cold, nutrient-rich deep water ceases to rise along the eastern boundaries of the ocean basins. The biological productivity of these regions, which currently supports not just fish, but whales, seabirds, and the entire marine food web connected to them, collapses as the nutrients stop rising to the sunlit surface layer where photosynthesis can occur. This is not a dramatic catastrophe like a wave or a wind. It is a quiet, slow failure of the ocean's fertilization system, occurring over years as the circulation reorganizes, with cascading consequences for marine ecosystems throughout the affected regions. This latitude dependence is crucial, and it means that the consequences of stopping Earth's rotation are not uniform across the planet. The equatorial regions, where the speed is highest, have the most kinetic energy to lose when the rotation stops. The polar regions, where the speed is near zero, are barely affected by the cessation of rotation itself. The equator is the danger zone. The middle latitudes are serious. The poles are comparatively quiet. But there is a consequence that affects the entire planet, every latitude, every location, and it is so fundamental that it needs to be established first before we can discuss any of the regional effects. That consequence is the shape of the Earth itself. Earth is not a perfect sphere. It is an oblate spheroid, flattened at the poles and bulging at the equator, like a slightly squashed ball. The equatorial radius of the Earth is 6,378 kilometers. The polar radius is 6,357 kilometers. The difference is 21 kilometers. The equatorial bulge, the extra 21 kilometers of radius at the equator compared to the poles, exists because the Earth is rotating, and the rotation creates a centrifugal effect that pushes material outward from the axis of rotation. The equatorial regions bulge outward, in response to this rotational flattening, and the shape of the Earth, its oblate spheroidal form, is a direct physical consequence of the rotation. This shape is not just a feature of the solid rock. The oceans, the atmosphere, and the mantle itself have all adjusted their distribution to this rotating equilibrium. The Earth's equatorial bulge is the planet's rotation, encoded in the planet's shape. If Earth stopped rotating, it would no longer need to be ablate. The equatorial bulge would have no physical justification. The centrifugal effect that maintains it would be gone. Over geological timescales, the solid Earth would slowly relax toward a more spherical shape, with material flowing from the equatorial regions toward the poles, driven by gravity. This process, the isostatic adjustment of the solid Earth to the new non-rotating equilibrium, would take millions of years for the full adjustment, because the mantle, though it flows on geological timescales, is extraordinarily viscous. But over those millions of years, enormous amounts of mass would redistribute. The seafloor and the continental crust would shift. Volcanism and seismic activity would be triggered by the changing stresses, and the planet would reshape itself for a world without rotation. In the immediate aftermath of an instantaneous stop, however, the shape of the Earth would be irrelevant to everything else happening, because everything else happening would be so catastrophically violent that geological reshaping would be a concern for millions of years later, not for the first days or years. So, let us return to the scenario we began with, the instantaneous stop. The scenario that is physically impossible. No known force in the universe could stop a planet's rotation in an instant without vaporizing it, but whose consequences are enormously clarifying about what rotation means for the structures on Earth's feet. Surface. The Earth stops instantaneously. What happens? Everything on the surface of the Earth that is not bolted to the bedrock, and many things that are, continues moving at the speed the surface was moving at the moment of the stop. At the equator, everything that was sitting on the surface is now moving at 1,674 kilometers per hour relative to the ground, faster than a typical rifle bullet, the speed of the fastest military jet aircraft ever built. Anything on the equatorial surface, buildings, soil, trees, water, cars, people, every artifact of human civilization is instantly launched eastward at this speed, sliding over a suddenly stationary ground, shredding, grinding, fragmenting, vaporizing through friction in the cases of softer materials, catastrophically colliding with anything that stands in its way. A city at the equator would be instantaneously destroyed, not by an explosion, but by inertia, by the simple fact that the city was moving and is no longer supported by the surface that was also moving. The buildings slide, they fragment. They create a massive eastward moving wave of debris, travelling initially at supersonic speeds, tearing up the landscape as they go. At higher latitudes, the same effect operates at lower speeds. At 45 degrees north, the initial eastward velocity is 1,180 kilometers per hour, still faster than the cruising speed of a commercial aircraft. Still catastrophic. At 60 degrees north, the velocity is about 835 kilometers per hour. At 70 degrees north, about 570 kilometers per hour. At 80 degrees north, about 290 kilometers per hour. Still catastrophic for any structure or organism on the surface. At the poles themselves, the velocity is essentially zero, and the immediate effects of the stop are minimal in this particular regard, though what happens to the poles in the days and years following the stop is severe in different ways. The atmosphere is in the same situation as the surface material. The lower atmosphere, the troposphere, which extends to about 12 kilometers altitude, is coupled to the surface through friction and is rotating with the Earth at roughly the same speed. When the Earth stops, the atmosphere continues moving eastward. At the equator, the entire troposphere and much of the stratosphere above it immediately becomes a 1,674 km/h wind, blowing in the direction that was previously east, tearing across a suddenly stationary surface. The wind speeds required to produce catastrophic erosion are typically measured in the range of a few hundred km/h for the most destructive hurricanes and tornadoes ever recorded. The strongest winds in Earth's recorded history, the surface gusts produced by nuclear weapons testing, and extreme tornadoes have reached around 500 km/h. The instantaneous stop scenario produces equatorial winds of more than 3 times that speed. This is not a weather event, it is a planetary-scale stripping of the surface. The wind does not immediately drop to zero as it moves over the landscape. It encounters the surface and is slowed by friction, creating enormous turbulent boundary layers hundreds of kilometers thick, generating heat through the viscous dissipation of the kinetic energy. Driving massive fire events where the wind's heat and friction ignite the vegetation and structures below. The kinetic energy of Earth's atmosphere alone is extraordinary. The atmosphere has a mass of about 5.15 times 10 to the power of 18 kilograms, and equatorial rotation velocities of 465 meters per second. Its kinetic energy is approximately 5.5 times 10 to the power of 2/3 joules. For reference, the most powerful earthquake ever recorded, the 1960 Valdivia earthquake in Chile, with a magnitude of 9.5, released approximately 10 to the power of 19 joules of seismic energy. The kinetic energy of Earth's atmosphere at equatorial rotation speed is about 50,000 times the energy of the largest earthquake ever recorded. All of that energy needs to dissipate into heat, into wave energy, into the grinding destruction of the surface as the atmosphere decelerates from 465 meters per second to zero. The ocean is worse in certain ways because it is denser and deeper. The average depth of the ocean is 3,688 meters. The total mass of the ocean is approximately 1.4 times 10 squared 1 kilograms. At equatorial rotation speeds, the kinetic energy of the ocean is approximately 1.5 times 10 squared 6 joules, merely 300 times the kinetic energy of the atmosphere alone. This energy, released as the ocean continues moving eastward, while the Earth's crust beneath it stops, would generate waves of incomprehensible size. Consider what an ocean wave requires. A normal wind-driven ocean wave draws its energy from the wind acting on the surface over some fetch of ocean. The largest wind-driven waves in recorded history, produced by the most powerful storms and sustained over the greatest distances, have reached heights of about 30 meters in extreme cases. Rogue waves of unusual height have been recorded at over 25 meters. These are produced by relatively modest energy inputs compared to the total ocean. Now consider the entire kinetic energy of the moving ocean, 1.5 times 10 squared 6 joules, being deposited into the wave as the ocean attempts to continue moving while the basin beneath it has stopped. The waves that would result are not waves in the conventional sense. They are the ocean, in bulk, moving eastward over the suddenly stationary seafloor. The water, no longer supported by the rotating frame of the Earth, surges toward the eastern shores of every continent, climbing far up onto land, travelling inland for hundreds of kilometres in the regions where the topography allows it, inundating coastal plains, river valleys, and low-lying regions on a scale that has no historical precedent. The height of the surge depends on the local topography. Steep coastal mountains might confine and deflect it. Flat coastal plains would allow it to travel inland almost without limit until friction and gravity slow it. The continental shelves, the shallow underwater plains extending from the coasts out to the edge of the continental slope, would become temporary land as the ocean surges eastward and the sea level on the western side of continental masses temporarily drops as the water rushes away. After the initial surge, the water would slosh back, creating oscillating megawaves that would continue for days or weeks, gradually losing energy to friction and turbulence, until the ocean found a new equilibrium in a non-rotating world. That new equilibrium would be dramatically different from the current one. In the current rotating world, the equatorial bulge that affects the solid Earth also affects the ocean. The water at the equator is pushed outward by the centrifugal effect and sits at a higher gravitational potential than the water at the poles. The ocean surface at the equator is actually about 21 kilometers farther from Earth's center than the ocean surface at the poles, not because the equatorial ocean is deeper, but because the entire shape of the Earth, ocean included, reflects the rotational flattening. In a non-rotating world, this bulge would slowly disappear. The ocean would drain from the equator toward the poles, and a new non-rotating ocean equilibrium would have the water distributed more uniformly across a more spherical Earth. The sea level at the equator would eventually drop by roughly 8 kilometers relative to the current level, not because the water disappears, but because the equatorial bulge relaxes and the water redistributes. Correspondingly, sea levels at the poles would rise. The poles would be underwater. The equatorial regions, after the ocean drains away, would be drier than they are today, vast new land masses emerging from the sea as the equatorial ocean retreats. But this long-term redistribution of the ocean takes millions of years of geological relaxation. In the short term, in the first hours, days and years after an instantaneous stop, the ocean is a catastrophic wave engine driven by its own kinetic energy, creating destruction on a scale no geological event in Earth's history has approached. Let us linger on the new equilibrium ocean for a moment, because it is one of the most transformative long-term consequences of the stopped rotation. And it produces a genuinely alien geography that would take millions of years to emerge, but would be the permanent face of a non-rotating Earth. The redistribution of the ocean from the equatorial bulge toward the poles, a consequence of the equatorial bulge relaxing toward a spherical shape, would expose an enormous band of new land around the equator. Consider the numbers precisely. The equatorial bulge gives the Earth's equatorial radius an extra 21 kilometers compared to the polar radius. The ocean surface mirrors this shape. In a non-rotating world, the ocean would redistribute until it sits in the gravitational potential well of a more spherical Earth. The precise amount of sea level change depends on how completely the bulge relaxes and on the distribution of the ocean between the current ocean basins. But rough calculations suggest that sea level at the equator would fall by approximately 8 kilometers relative to today, while sea level at the poles would rise by a comparable amount. The poles, currently above sea level, and the land masses of Greenland and Antarctica, or covered by relatively shallow Arctic Ocean, would be submerged under hundreds of meters of water. The equatorial regions, currently partly covered by the tropical Pacific and Atlantic and Indian Oceans, would have vast new land masses emerging from the sea. The new equatorial land would emerge from the western tropical Pacific, an enormous shallow region currently covered by warm tropical water, and from the equatorial Atlantic and Indian Oceans. The geography that emerged would be unlike anything in Earth's current atlas. A planet with dry polar deserts where no land exists today, covered instead by permanent polar seas, and a dry equatorial supercontinent stretching around the tropics where the deep tropical ocean currently sits. The current continental configurations, the Americas, Europe, Africa, Asia, Australia, would be dramatically altered as their coastal regions were exposed or inundated. Much of what is currently coastal lowland, the Amazon basin, the Ganges plain, the coastal cities of every major civilization, would be submerged as the polar seas rose. Much of what is currently the tropical Pacific floor would become exposed land, initially lifeless, but gradually colonized if life survived elsewhere. This restructuring is not just a consequence of the water redistribution. It is also a consequence of the solid Earth's response to the changed stress regime. The equatorial bulge is not only in the ocean. It is in the mantle, in the crust, in the entire structure of the planet. As the rotation slows and stops, the mantle begins to flow toward the poles, carrying the crust with it. Regions of the equatorial crust subside as the mantle beneath them flows away. Regions of polar crust rise as mantle material flows toward them. The pattern of iastatic adjustment would create new topography, new mountain ranges at unexpected latitudes, new basins where none existed. It would trigger volcanism, not just at existing volcanic zones but along new zones of stress concentration, and it would reactivate fault systems throughout the equatorial and middle latitudes that have been quiet for millions of years. The geological map of a non-rotating Earth would, over millions of years, bear little resemblance to the geological map we know today. Throughout this process, the erosive forces that shape the landscape would also be different. Without the Coriolis effect, there would be no organized jet streams to drive moisture from the oceans deep into continental interiors. The distribution of rainfall would be determined by the much simpler dynamics of a non-rotating atmosphere. Rainfall concentrated at the substellar point, in the permanent storm system over the dayside and along the terminator ring. The continental interiors of the dayside would be deserts, because the moisture-carrying circulation would not penetrate far inland. The continental interiors of the night side would be frozen deserts, because the temperature would be too low for liquid water to exist. Only the terminator regions, the perimeter of the planet where day and night meet permanently, would have the combination of temperature, moisture, and light that currently characterizes the broad habitable middle latitudes. The continental shelf regions that would emerge from the sea as the equatorial ocean drained would initially be barren, deep sea sediments exposed to air, rich in organic material from billions of years of marine biological productivity, but uninhabitable for terrestrial life until soil chemistry and ecosystems developed. The process of colonizing these new equatorial lands, if life survived in the terminator zone, would take thousands to millions of years. The timescale of colonization would depend on the pace of soil formation, the availability of fresh water, which would come from condensation and from precipitation transported from the dayside by the atmospheric circulation, and the evolutionary flexibility of the surviving organisms. It is a world that has never existed in Earth's history, a world unlike any planet we have observed, a world that would take millions of years to develop its own character and ecology. But it is the world that the physics of a stopped rotation would eventually produce, given enough geological time. Let us leave the instantaneous scenario now, having established the physical forces in play, and move to something important that the instantaneous scenario did not adequately address: the effect on Earth's magnetic field. Because this consequence, slower than the sloshing of the ocean and the movement of the atmosphere, is in some ways the most significant for the long-term habitability of the planet. Earth has a global magnetic field. The geode Earth has a global magnetic field that extends from within the Earth's interior, deflecting charged particles from the solar wind and shielding the planet's surface from the bombardment of high-energy cosmic rays. You know this field from compasses. The field is roughly aligned with Earth's rotation axis, with a magnetic north pole near the geographic north pole and a magnetic south pole near the geographic south pole. The field is not a permanent magnet. The Earth is far too hot inside for permanent magnetism, since most magnetic materials lose their magnetic properties above a temperature called a Curie point, and the Earth's interior is far above that. Instead, the geomagnetic field is generated by a geodynamo, the churning, convective motion of molten iron in Earth's outer core, combined with the Earth's rotation, produces electric currents that generate the magnetic field through a process similar to the electromagnetic induction in a generator. The outer core of the Earth, the liquid iron layer between roughly 2,098 and 5,150 kilometers from the center, is the seat of the geodynamo. The molten iron in the outer core is both an excellent electrical conductor and subject to convective motion driven by the heat flowing outward from the inner core and by the compositional convection produced as the inner core solidifies. This convective motion, operating in the presence of Earth's rotation, is organized by the Coriolis effect, the rotational deflection of fluid motions that also organizes hurricanes and ocean currents on the surface into coherent helical flows that efficiently generate and sustain the magnetic field against the Coriolis effect, resistive losses that would otherwise decay it. The rotation of the Earth is not merely incidental to the geodynamic, it is fundamental. The Coriolis effect organizes the outer core's convective flows into the columnar structures that make the geodynamo work. Without the Coriolis effect, which requires rotation, the convective motions would be disordered and much less efficient at generating and sustaining a magnetic field. If Earth's rotation slows or stops, the Coriolis effect weakens or disappears. The organized helical columns of the geodynamo lose their coherence. The geodynamo becomes less efficient. Over time, not immediately, because the geodynamo has its own inertia and the magnetic field has its own persistence, the geomagnetic field weakens. Okay. The timescale for the magnetic field to respond to a change in core dynamics is not the same as the timescale for the rotation to stop. Even if the rotation stopped instantaneously, the magnetic field would not immediately vanish. Okay. The geodynamo's timescale, the time it takes for the field to decay to half its current strength if the generating mechanism was shut off, is roughly 15,000 to 20,000 years. This is called the magnetic diffusion timescale, and it is set by the electrical conductivity of the outer core material and the size of the core. So after an instantaneous stop, the magnetic field would persist for thousands of years, slowly weakening as the now disorganized convection in the outer core fails to regenerate it. After several tens of thousands of years, the geomagnetic field would have declined to a fraction of its current strength, and eventually, unless some other mechanism generates a magnetic field, it would approach zero. At that point, the Earth would be exposed to the full force of the solar wind, the stream of charged particles, primarily protons and electrons, expelled from the Sun at speeds of 400 to 800 kilometers per second. The solar wind, undeflected by the geomagnetic field, would impinge directly on the upper atmosphere and begin a process that has already been observed on another planet, atmospheric erosion. Mars is the most relevant case study. Mars lost its global magnetic field roughly 4 billion years ago, probably because its smaller iron core cooled and solidified, stopping its geodynamo. The story of how we know this is itself extraordinary. When the Mars Global Surveyor spacecraft entered orbit around Mars in 1997 and began mapping the planet's magnetic field with an onboard magnetometer, it found something unexpected. The planet had no global magnetic field, no dipole extending into space, no magnetosphere protecting the planet. What it found instead were magnetic anomalies in the ancient southern highlands, localized, striped regions of the crust that were magnetized like frozen compass needles, recording the direction of the magnetic field at the time the rocks cooled through the Curie point billions of years ago. These remnant magnetic anomalies are the fossil of Mars's ancient global magnetic field, preserved in the oldest, most ancient terrains on the planet, the regions that cooled and solidified before the magnetic field switched off. The younger terrains, the volcanic plains and impact basins of the northern lowlands, show no such remnant magnetism. They cooled after the geodynamo had already stopped, and they recorded nothing. The Mars Global Surveyor magnetometer effectively read Mars's magnetic autobiography, a planet that once had a global field, that recorded the direction of that field in its oldest rocks, and that then lost the field and cooled into silence. Without a magnetic field, Mars had no protection against the solar wind. Over billions of years, the solar wind has gradually stripped away Mars's atmosphere, the most energetic solar particles, and UV radiation ionizing and heating the upper atmosphere, while the magnetic force of the solar wind carries ionized gas away from the planet. The MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, which entered Mars orbit in 2014, has directly measured the rate of atmospheric escape from Mars today, measuring the flux of ions being swept away by the solar wind at approximately 100 grams per second. At this rate, over billions of years, trillions of tons of atmosphere have been lost to space. Mars today has an atmospheric pressure at the surface of about 0.6% of Earth's, a thin, cold, essentially unbreathable mixture of carbon dioxide. Mars almost certainly once had a denser atmosphere and possibly liquid water on its surface. The loss of the magnetic field and the subsequent atmospheric erosion by the solar wind is one of the leading explanations for Mars's transformation from a potentially habitable world to the frigid desert we observe today. Contrast Mars with Venus. Venus, Earth's other neighbour, has roughly the same size and mass as Earth, about 95% of Earth's radius and 81% of Earth's mass. But Venus rotates extraordinarily slowly. It completes one rotation in about 243 Earth days, in the retrograde direction, that is, in the opposite sense from Earth's rotation, so the Sun rises in the west on Venus and sets in the east. The reason for Venus's slow and retrograde rotation is still debated, but one leading hypothesis involves a large impact or resonance interaction early in solar system history that reversed its spin. The important point for our discussion is that Venus, despite rotating very slowly, does have a magnetic field, but it is a very weak, induced magnetic field generated by the interaction of the solar wind with Venus's ionosphere, not a true internally generated geodynamic field. Venus appears to lack a dynamo entirely, probably because the planet's core is not convecting efficiently enough to drive one. Possibly because Venus lacks the plate tectonics that facilitate heat loss from Earth's mantle and thus the temperature gradient that drives outer core convection. The consequence is that Venus, despite being nearly Earth's twin in size and composition, is exposed to the solar wind in a way Earth is not. The solar wind impinges on Venus's upper atmosphere and drives atmospheric escape, though not as dramatically as on Mars, because Venus's stronger gravity and denser atmosphere make escape harder. Venus still has a thick atmosphere. In fact, an extraordinarily thick one, with surface pressure 92 times Earth's. But this thick atmosphere is not primarily the result of good magnetic shielding. It is a result of the intense volcanic outgassing that has resupplied the atmosphere with carbon dioxide over geological time, overcoming the loss from the top. Venus's atmosphere is a different thing from Earth's atmosphere. It is a runaway greenhouse catastrophe, with surface temperatures of 465 degrees Celsius and sulfuric acid clouds, entirely inhospitable by any measure. But it is present. The comparison with Mars illustrates that planetary size and atmospheric resupply rate matter as much as magnetic field strength for long-term atmospheric retention. Earth without its magnetic field would not lose its atmosphere as quickly as Mars did. Earth is larger, with stronger gravity, and the solar wind's ability to remove atmospheric molecules depends on the ratio of the energy the solar wind delivers to the kinetic energy needed to escape the planet's gravity. For Earth, the timescale for significant atmospheric erosion without a magnetic field is estimated at hundreds of millions to billions of years, rather than the much faster geological timescale on Mars. But hundreds of millions of years is not a comfort, it is a sentence. In the absence of a magnetic field, Earth would be a different kind of dangerous place, within human-relevant timescales. The immediate consequences of a weakening magnetic field are more pressing than the long-term atmospheric erosion. The magnetic field currently deflects the solar wind around the planet, confining it to a region of space called the magnetosphere, a teardrop-shaped bubble extending roughly 10 Earth radii on the sunward side and stretching to a long tail on the opposite side. Within the magnetosphere, charged particles from the solar wind are trapped in the Van Allen radiation belts, two torus-shaped regions of intense radiation surrounding the Earth, lying within the magnetosphere. The inner belt, at altitudes of roughly 1,000 to 6,000 kilometers, is populated primarily by high-energy protons. The outer belt, at 15,000 to 25,000 kilometers, contains high-energy electrons. These radiation belts are normally held in place by the magnetic field and do not touch the surface. As the magnetic field weakens, whether instantaneously from a rotation stop or gradually over thousands of years, the Van Allen belts diffuse downward toward the surface, and the shielding against cosmic rays from outside the solar system diminishes. The cosmic ray flux at Earth's surface would increase significantly. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, traveling at close to the speed of light, originating from supernovae and other energetic events in the galaxy. At current levels, cosmic rays contribute to the background radiation dose received by humans, but at levels that are manageable for biological systems. An increase in cosmic ray flux by a factor of 10 or more, as might occur with a substantially weakened magnetic field, would significantly increase mutation rates, increase cancer risks, and threaten the stability of the genetic information in all surface-dwelling organisms. The ozone layer, which shields the surface from ultraviolet radiation, is partly maintained by photochemical processes that depend on the current balance of atmospheric chemistry. A higher cosmic ray flux would disrupt some of these processes, potentially thinning the ozone layer and allowing more damaging ultraviolet light to reach the surface. None of this kills all life immediately. Life on Earth has existed through periods of geomagnetic reversal, events in which the north and south magnetic poles switch places, during which the field weakens substantially, sometimes declining to as little as 10% of its current strength. These reversals last thousands of years each and occur with some frequency in Earth's geological history, roughly every 300,000 years on average. Though the timing is irregular, and the last full reversal was about 780,000 years ago. Life has survived these reversals without mass extinctions, suggesting that the reduced magnetic field during reversals, while stressful, is not catastrophically lethal. A permanent loss of the magnetic field is a different matter, not because the immediate effects are so much more severe, but because they are permanent rather than temporary. There is no recovery from a permanent magnetic field loss, no flip back to a strong field. The degradation of the atmospheric shield is one-directional and cumulative. There is a poignant and beautiful consequence of the magnetic field loss that is worth noting. Not because it is catastrophic, it is not, but because it illustrates the intimate connection between Earth's field and the phenomena we find most visually extraordinary. The auroras, the northern and southern lights, the curtains and ribbons of green and red and blue light that shimmer above the polar regions on clear nights, are produced by the magnetic field. They occur when energetic particles from the solar wind and from solar coronal mass ejections follow the magnetic field lines toward the polar regions and collide with nitrogen and oxygen molecules in the upper atmosphere, exciting them to higher energy states that then release light as they return to their ground states. The green aurora is oxygen at about 100 kilometers altitude. The red aurora is oxygen at higher altitudes where the density is lower and the transition takes longer. The blue and purple aurora is nitrogen. The specific colours and shapes of the aurora are a map of the atmospheric chemistry and the magnetic field geometry that guides the particles. Without the magnetic field, there would be no auroras. The solar wind particles would no longer be funneled toward the poles along magnetic field lines. They would instead be deflected by the atmosphere directly, producing a diffuse glow across the entire upper atmosphere, not the sharp, dynamic curtains and ribbons of the aurora, but a uniform, featureless dim luminescence. The transformation of the night sky from a place where the aurora sometimes dances to a place where it never does would be, on its own, one of the most profound changes that the loss of Earth's magnetic field would bring. Thousands of years of human poetry, art, mythology, and wonder directed at the northern lights would have nothing in the sky to point at. And on the practical side, the loss of the magnetic field would make solar events far more dangerous than they currently are. The sun periodically emits coronal mass ejections, enormous eruptions of magnetized plasma from the solar corona, traveling outward through the solar system at speeds of hundreds to thousands of kilometers per second. When a large CME strikes Earth's magnetosphere, it can cause a geomagnetic storm, a temporary disturbance of the magnetic field that can induce large electrical currents in the ground and in long conductors like power lines and pipelines, potentially disabling power grids and communication systems. The 1989 Quebec blackout was caused by a moderate geomagnetic storm. The even more powerful Carrington event of 1859, which occurred before the electrical grid existed, would have caused catastrophic damage to modern infrastructure if it happened today. Without the magnetic field, a large CME would not produce a geomagnetic storm. It would produce something worse. The plasma of the CME would interact directly with the upper atmosphere, delivering its energy not through magnetic induction, but through direct particle bombardment and heating of the ionosphere and stratosphere. The ozone layer would be particularly vulnerable. Energetic particles penetrating the stratosphere produce nitrogen oxides that catalytically destroy ozone, and a large CNE hitting an unshielded Earth could deplete stratospheric ozone significantly in the polar regions, allowing increased ultraviolet radiation to reach the surface. Multiple large CMEs over years or decades could cumulatively damage the ozone layer, reducing UV protection for surface life across the planet. The Sun is not a steady, benign energy source. It is an active, variable star that periodically erupts with extraordinary energy. Earth's magnetic field is the shield that makes the difference between those eruptions being manageable weather events and being existential threats to the surface biosphere. We have been discussing the consequences of Earth stopping in the context of the planet's physical systems, the motion of the surface, the atmosphere, the ocean, the magnetic field. But we have not yet discussed the most profound consequence of a world that is no longer rotating, and it is one that operates not through catastrophic violence, but through a slow, inexorable change in the thermal regime of the planet. It is the consequence that would define what life on a non-rotating Earth would look like, assuming life survived the initial catastrophe. And it is this: without rotation, there is no day-night cycle. One hemisphere faces the sun permanently. The other hemisphere faces eternal darkness. Before exploring this, let us be precise about what one side faces the sun means for the thermal and atmospheric structure of the planet. It does not mean, as it might initially seem, that the sunlit hemisphere simply becomes warm and the dark hemisphere simply becomes cold. The atmosphere is a fluid, and fluids transport heat. The question is, how much heat the atmosphere can transport from the sunlit side to the dark side, and what the equilibrium temperature distribution would be in the absence of rotation to drive the familiar global circulation patterns we have today. In the current rotating Earth, the general circulation of the atmosphere is driven by two things: the differential heating between the equator, which receives the most solar energy, and the poles, which receive the least, and the Coriolis effect, imposed by the rotation. The Coriolis effect deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere, breaking the single global convection cell that would otherwise exist. A simple, large-scale overturning circulation with warm air rising at the equator, moving toward the poles, descending and returning into the complex, banded system of trade winds, westerlies, and polar easterlies that we observe. The Hadley cells, Ferrel cells, and polar cells of the global atmospheric circulation are all products of the Coriolis effect, organizing the temperature-driven overturning into a multi-cell structure. Remove the rotation, and with it the Coriolis effect, and the global circulation changes fundamentally. Instead of the banded zonal circulation, driven partly by the day-night cycle and partly by the equator pole temperature gradient, you would have a circulation driven by the day-night temperature difference. A single global overturning cell with warm air rising on the sunlit side, flowing toward the dark side at high altitude, cooling and sinking on the dark side, and returning along the surface back toward the warm side. The result, worked out in detail in the atmosphere of tidally locked planets orbiting other stars, which are the closest real-world analogue to a non-rotating Earth, is a permanent storm system centered on the substellar point, the point on the surface directly beneath the Sun, with persistent inflow of cold air from the dark side converging toward the warm side and driving convective uplift at the center. A temperature contrast between the day and night sides would be enormous, perhaps hundreds of degrees, in the absence of atmospheric circulation. But the circulation moderates this. General circulation models of tidally locked Earth-like planets suggest that atmospheric transport can keep the day side from becoming uninhabitably hot and the night side from freezing completely, especially if the atmospheric pressure is similar to Earth's current value. The dayside surface temperature at the substellar point might stabilize around 60 to 80 degrees Celsius, hot enough to be uncomfortable for most life, but not globally sterilizing. The night side would be extremely cold, perhaps minus 50 to minus 100 degrees Celsius at the antipodal point, but would not necessarily freeze all the way down to the poles of the night side, because atmospheric heat transport would maintain a temperature above the condensation point of carbon dioxide in most of the night side. The terminator, the line between the permanent day side and the permanent night side, will be a permanently twilit zone of moderate temperatures, constant winds, and perpetual sunrise-sunset light angles. This terminator ring might actually be the most habitable zone on a tidally locked Earth, warm enough for liquid water, not so hot as to be uninhabitable, lit by a sun that never rises above the horizon, experiencing a permanent golden hour of early morning light. It would be a strange world, a world of constant wind as the atmospheric circulation sweeps cold night-side air toward the warm day side and back again, of light that never changes angle, of a sun that sits motionless on the horizon from every point on the terminator, but not necessarily a dead world. The ocean, in the non-rotating scenario, would also change dramatically. Currently, the rotation of the Earth and the Coriolis effect drive the great ocean gyres, the large-scale circular currents of the Atlantic, Pacific, Indian, and Southern Oceans, as well as the thermohaline circulation, the deep, overturning circulation that carries warm surface water toward the poles and cold deep water back toward the equator, redistributing heat and moderating the climate of the high latitudes. Without rotation, the ocean currents would lose their gyre structure. The circulation would be driven instead by the day-night temperature contrast and by the temperature difference between the permanent sunlit side and the permanent dark side. The ocean would develop a circulation pattern analogous to the atmosphere's, flowing along the surface from the cold night side toward the warm day side, sinking as it is heated at the substellar point, flowing back along the deep ocean floor, upwelling on the night side. The redistribution of heat by this circulation would help moderate the extreme temperatures that would otherwise develop on both sides. The terminator line, where ocean and atmosphere meet the permanent sunset, would likely be a zone of intense precipitation. The warm, moist air from the day side, carried aloft by the circulation, cools as it moves toward the terminator and the night side, releasing its moisture as rain, and, further into the night side, as snow. The terminator might be a permanent rainfall zone, green and well-watered, if the circulation delivers sufficient moisture. The deep night side would be desert, dry, cold, and dark, because all the moisture would have precipitated out before reaching the antipodal region. This is the world that emerges eventually from an Earth that is stopped rotating. Not an instantaneous catastrophe, but a long-term transformation from a world of day and night, of seasons, of trade winds and gyres, and a 24-hour rhythm that all life on Earth has evolved to depend on, to a world of permanent hemispheres, of a sunlit side and a dark side, of a terminator ring that may be the only habitable margin of a transformed planet. The transformation is gradual enough, taking millions of years for the geological adjustments, and perhaps hundreds of thousands of years for the atmospheric and oceanic circulation to settle into new patterns, that life would not necessarily be extinguished entirely, but it would be radically, permanently different. Now let us talk about the scenario that is physically realistic, not the instantaneous stop, but the gradual slowing. Because Earth's rotation is, in fact, slowing. Not quickly, not in any way that would be perceptible in a human lifetime, or even in 1,000 human lifetimes, but measurably, irreversibly, and for a reason that is important to understand. Earth's rotation is slowing because of tidal friction. The gravitational pull of the Moon, and, to a lesser extent the Sun, raises tides in Earth's oceans and, to a smaller degree, in the solid rock of the planet itself. These tidal bulges are not perfectly aligned with the Moon, because the rotating Earth carries the tidal bulges ahead of the Earth-Moon line as the planet rotates faster than the Moon orbits. The tidal bulge on the side of the Earth facing the Moon is displaced slightly in the direction of rotation, and this displaced bulge exerts a small gravitational torque on the Moon, pulling it slightly forward in its orbit and transferring angular momentum from Earth's rotation to the Moon's orbital motion. The Moon slowly spirals outward, gaining orbital energy and moving to a larger orbit, while Earth's rotation slowly loses angular momentum and slows. The current rate of slowing is approximately 1.4 milliseconds per century. The length of the day increases by about 1.4 milliseconds every 100 years. This is a tiny change. In a human lifetime, the day lengthens by roughly 0.01 milliseconds, completely imperceptible to any biological timekeeping. But over geological timescales, this slow drift accumulates to significant changes. 4 billion years ago, when life was just beginning on Earth, the day was approximately 6 hours long. The proto-Earth was rotating about 4 times faster than it does today, and the Moon was much closer. Perhaps only 20,000 to 30,000 kilometers away, compared to the current 384,000 kilometers. As the Moon receded and Earth's rotation slowed, the day lengthened, eventually reaching the current 24 hours after about 4.5 billion years of tidal braking. We know this not just from theoretical calculation, but from the geological record. Ancient tidal rhythmites, sedimentary deposits formed by tidal action in shallow coastal environments, preserve a record of the tidal cycle at the time of their deposition. By counting the thin laminations within each tidal bundle, geologists can determine how many tidal cycles occurred per year, and from this, calculate the length of the day when those sediments were deposited. Tidal rhythmites from the Precambrian, dating to about 620 million years ago and found in the Ilatina Formation in South Australia, record approximately 400 days per year, meaning the day was about 22 hours long at that time. Even older samples, dating to about 2.5 billion years ago, record days of roughly 16 to 18 hours. The geological record confirms what the physics predicts. The Earth has been spinning down for its entire history, the day growing longer as the Moon recedes. The fossil record of daily growth patterns in ancient organisms provides a complementary line of evidence. Corals, bivalves, and other organisms with hard shells record daily and annual growth rhythms in their shells, the way a tree records growth seasons in its rings. Ancient coral fossils from the Devonian period, about 380 million years ago, show approximately 400 daily growth increments per year, consistent with a 22-hour day and about 400 days in the Devonian year. The coral did not know it was recording the length of the Earth's day. It was simply growing, responding to the day-night cycle, one thin growth layer per day, year after year for its entire life, and when it died and was preserved in sediment, it left behind a diary of deep time. Each layer is a day in a world that no longer exists, a world rotating slightly faster than ours, under a moon slightly closer than ours, its tides slightly higher, its days slightly shorter. Imperceptibly different from our world, but measurably so across geological time. The moon is currently receding from Earth at approximately 3.8 centimeters per year, a rate measured with extraordinary precision by the Lunar Laser Ranging Experiment, in which astronomers fire lasers at retroreflectors placed on the lunar surface by the Apollo astronauts and measure the round-trip travel time of the light pulse. The retroreflectors are still there and still in use. Scientists have been measuring the moon's recession since 1969, accumulating decades of data that confirm the tidal friction model with remarkable precision. The moon is moving away. The Earth is slowing down. The night the first Apollo astronaut placed the first retroreflector on the lunar surface, humanity gained the ability to measure one of the most fundamental long-term processes shaping our planet, the slow or ancient deceleration of the world's rotation by the gravitational reach of its moon. In a few billion more years, if the tidal friction continues and if the sun's expansion doesn't intervene first, Earth's rotation would eventually synchronize with the moon's orbital period, a state called tidal locking, in which the same face of the Earth always faces the moon, just as the same face of the moon always faces the Earth today. At that point, Earth's rotation would not stop entirely, but it would slow to approximately the moon's current orbital period of about 27.3 days. The day would be 27 times longer than it is today. But this endpoint is relevant not just as a distant future scenario, but as a present reality for other worlds in our solar system and beyond. Tidal locking is, in fact, the default state for many planetary bodies. And understanding what it produces gives us insight into how Earth's rotation shapes its current character. By contrast, but this endpoint, if Earth were tidally locked to the moon, is not the same as a fully stopped rotation. Earth would still be rotating once every 27.3 days. There would still be a day-night cycle, just an extremely long one. The consequences of a 27-day day are significant, but not catastrophic in the way a fully stopped rotation would be. With a 27-day day, the day side of Earth would receive continuous sunlight for almost 2 weeks before the planet rotated the night side into sunlight. Temperatures on the day side would build significantly during those 2 weeks, perhaps reaching 50 to 60 degrees Celsius in tropical regions before the rotation brought night side cooling. The night side would cool during its 2-week darkness, but not to the extreme temperatures of a permanently dark hemisphere, because the day would eventually return. The diurnal temperature range, the difference between daytime and nighttime temperatures, would be enormous, perhaps 100 degrees or more in continental interiors. The atmospheric circulation would also change dramatically. With such a slow rotation, the Coriolis effect would be greatly reduced, and the banded jet stream structure that currently organizes weather patterns would weaken. Weather systems would be larger, slower, and more persistent. Hurricanes and cyclones, which derive part of their structure from the Coriolis effect, would change character, potentially becoming larger, more diffuse systems rather than the tight, rapidly spinning vortices we know today. The ocean circulation would also be affected. The great gyres that currently transport heat from the tropics toward the poles are driven in part by the Coriolis effect. The gyres are a great canema. A weaker Coriolis effect from slower rotation would produce weaker, more sluggish gyres, and the thermohaline circulation would carry a larger relative role in heat transport. The climate would be warmer in polar regions and cooler in tropical regions relative to the current climate, as the reduced gyre-driven transport from tropics to poles is compensated by changes in the atmospheric circulation. For life, a 27-day day would be a significant challenge. Essentially, all of Earth's life has evolved with a 24-hour day-night cycle, and most organisms have circadian rhythms, internal biological clocks, tuned to this period. The sudden shift to a 27-day cycle would disrupt virtually every organism's circadian biology. But this shift would not happen suddenly. It would happen over billions of years, with the day lengthening by 1.4 milliseconds per century, so slowly that evolution would have ample time to adjust. Over billions of years, life would adapt, as it has adapted to every change in the Earth's environment over geological time. The Sun, however, will not wait for billions of years. The Sun is currently about 4.6 billion years old and will remain a stable main sequence star for another approximately 5 billion years. During this time, it will slowly brighten. The solar luminosity increases by about 1% every 110 million years as the Sun's helium fraction increases and the core contracts slightly. In about 1.1 billion years, the Sun will be bright enough, but the increased energy input will overwhelm the ability of the carbon silicate weathering cycle, Earth's primary long-term thermostat, to keep temperatures cool enough for liquid water at the surface. The Earth will become too hot for liquid water, and the oceans will begin to evaporate. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets, possibly including Earth, depending on the Sun's mass loss and Earth's orbital response. The question of whether Earth's rotation will ever reach zero through tidal locking is therefore moot in a practical sense. The Sun will transform the solar system long before Earth's rotation slows to zero. But the physics of the gradual slowdown is real, and it tells us something important about the role of rotation in maintaining the conditions we experience. The current 24-hour day is not fixed, not eternal, not guaranteed. It is a moment in the long deceleration of a spinning planet, a snapshot of a process that began with the Earth's formation and will continue until some external event, the Moon's recession, the Sun's expansion, a collision, changes the trajectory. Let us now return to the intermediate scenario that is most scientifically instructive, not the instantaneous stop and not the glacial tidal deceleration, but a scenario in which the Earth's rotation slows to a stop over a period of years to decades. Slow enough that the atmospheric and oceanic systems have time to begin adjusting, but fast enough that the disruption is severe within human timescales. This is not a physically realistic scenario. There is no mechanism in nature that produces this kind of rapid but non-instantaneous stopping, but it is useful for understanding which systems respond quickly and which respond slowly, and therefore which changes would be experienced by a civilization trying to survive the transition. In this scenario, call it the decade-scale stop, the first consequences would be felt in the atmosphere and ocean circulation. As the Coriolis effect weakens, because the Coriolis acceleration is proportional to the rotation rate, the jet streams and trade winds begin to lose their structure. The jet streams are the fast-moving bands of westerly wind at altitudes of roughly 8 to 12 kilometers that steer weather systems across the middle latitudes. They exist because of the temperature difference between the equatorial and polar regions, combined with the Coriolis effect. As the Coriolis effect weakens, the jet streams meander more wildly, break down into more chaotic patterns, and eventually dissolve. The organised weather systems that the jet streams steer, the extratropical cyclones that bring the rainfall that most of the world's agriculture depends on, lose their organiser. Weather patterns become increasingly erratic. Rainfall becomes less reliable. Droughts and floods become more severe and less predictable. The ocean gyres, the North Atlantic gyre, the North Pacific gyre, the South Atlantic and South Pacific gyres, the Indian Ocean gyre, begin to slow and eventually reverse their current patterns. The Gulf Stream, the North Atlantic Current, and the other poleward flowing surface currents that currently carry warm tropical water toward Europe and eastern North America, moderating the climate of those regions, weaken and eventually stop or reorganize. The climate of northwestern Europe, currently warmed by the Gulf Stream to temperatures far higher than its latitude would otherwise support, begins to cool substantially, approaching the temperatures that continental regions at similar latitudes like eastern Canada and Siberia currently experience. It is worth pausing here to appreciate what the Gulf Stream and the broader Atlantic thermohaline circulation actually represent, because they are one of the most dramatic consequences of Earth's rotation in the ocean. The Gulf Stream is a western boundary current, a fast, narrow, deep ocean current, flowing northward along the eastern coast of North America at approximately 2.5 meters per second, driven by the North Atlantic gyre. The North Atlantic gyre is driven by the trade winds in the tropics and the westerly winds in the middle latitudes, both products of the Coriolis effect acting on the temperature-driven atmospheric circulation. The Coriolis effect deflects winds and currents to the right in the northern hemisphere, driving a clockwise gyre of surface water, whose western boundary, the Gulf Stream, flows northward along the coast, carrying enormous amounts of heat. The Gulf Stream carries approximately 30 million cubic meters of water per second at its origin near Florida, increasing to about 150 million cubic meters per second as it flows north. The total freshwater discharge of all rivers on Earth combined is about 1.2 million cubic meters per second. The Gulf Stream alone carries more than 100 times the combined river discharge of the entire planet. The difference in climate between Western Europe and Eastern Canada at the same latitude, London and Edmonton, Alberta, are both near 51 degrees north, but London has mild winters, while Edmonton regularly sees minus 20 degrees Celsius, is largely attributable to the Gulf Stream and North Atlantic Current. Stopping it would impose Canadian prairie winters on England, France, Germany, and Scandinavia within decades. Beyond the surface current, the deeper thermohaline circulation, the Atlantic Meridional Overturning Circulation, or AMOC, is also dependent on rotation-driven processes. In the North Atlantic, the warm, salty surface water, carried northward by the Gulf Stream, loses heat to the atmosphere and becomes dense enough to sink to the deep ocean in the Labrador Sea and the Nordic Seas. This dense, cold, salty water flows southward along the deep Atlantic floor, eventually upwelling in the Southern Ocean and the tropical Atlantic. The entire conveyor belt depends on the density contrast maintained by the heat transport of the surface gyres, which depends on the Coriolis-driven winds, which depends on Earth's rotation. Remove the rotation, and the entire chain unravels, not instantly, but within years to decades. The tropics, deprived of the poleward export of heat by the weakening gyres, begin to warm. The equatorial Pacific, currently cooled by the upwelling of cold deep water, driven partly by the trade winds, also begins to change. As the trade winds weaken, with the diminishing Coriolis effect, the upwelling weakens, The equatorial Pacific surface warms, and conditions resemble a permanent extreme El Niño, with all the disruption to global weather patterns that severe El Niño events currently produce, multiplied and made permanent. The monsoons, the seasonal reversal of winds that brings rainfall to South Asia, West Africa, and other tropical regions, on which billions of people depend, also change character. Monsoons are driven primarily by the temperature difference between the land and the ocean, enhanced and organised by the Coriolis effect. As the Coriolis effect weakens, the monsoon circulation loses its organising structure, becoming less reliable, more spatially diffuse, and more temporally erratic. For the populations of South Asia, Sub-Saharan Africa, and East Asia that depend on monsoon rainfall for agriculture, this would be catastrophic. The agricultural systems that feed billions of people are calibrated to the current monsoon patterns, and a major disruption would threaten food security on a scale that no historical drought or famine has approached. These atmospheric and oceanic changes would occur over years to decades, in the decade scale. Stop. Scenario: fast enough to be experienced within human lifetimes, slow enough to allow recognition of what is happening, but not slow enough for adaptation to proceed. The agricultural disruptions would drive massive food shortages within years. The climate disruptions would be severe within decades. The civilization-scale consequences, the collapse of food production systems, the mass migration of populations from regions made uninhabitable by the new climate patterns, the loss of the trade wind systems that have historically enabled maritime commerce, would be profound. All of this, and we have not yet addressed, the seismic consequences. The Earth's rotation exerts a centrifugal effect, not just on the ocean and atmosphere, but on the solid Earth itself, on the crust, the mantle, and even the core. The equatorial bulge of 21 kilometers that we discussed earlier is maintained in equilibrium, partly by the centrifugal effect of the rotation and partly by the mantle's viscous resistance to change. As the rotation slows, the centrifugal effect diminishes and the equilibrium shape shifts. The mantle wants to flow toward the poles, reducing the equatorial bulge, as the equatorial regions are no longer being supported by the centrifugal force. This iostatic readjustment of the mantle creates new stress patterns in the crust, new regions of tension and compression, new fault systems, new seismic activity. The rate at which the mantle can flow, and therefore the rate at which the seismic activity would ramp up, depends on the viscosity of the mantle, which is roughly 10 squared 1 Pascal seconds in the upper mantle. This is extraordinarily viscous, 10 trillion times more viscous than water, but not infinitely so. Over thousands to millions of years, even this viscous fluid flows in response to changing stress. I love that. In the decade scale stop scenario, the mantle cannot flow fast enough to keep up with the changing rotation rate. The stress accumulates in the crust faster than it can be relieved by slow mantle flow, and the result is intense seismic activity. Major earthquakes become more frequent as new faults form and old ones are reactivated by the changing stress regime. The equatorial regions, where the reduction in centrifugal support is greatest, would experience the most intense seismicity, a global belt of earthquake activity around the equator, driven not by the movement of tectonic plates, but by the stress generated as the planet reshapes itself for a lower rotation rate. The volcanism would also increase. Volcanic eruptions on Earth are driven primarily by the movement of tectonic plates, the melting of subducting oceanic crust, the rifting of divergent plate boundaries, the hot spots driven by mantle plumes. These processes are not directly driven by Earth's rotation, but the increased seismic activity generated by the changing stress regime can trigger eruptions at volcanoes that are already in a marginal state, where the pressure of magma in the chamber is close to the strength of the overlying rock, needing only a small additional stress to fracture the crust and allow the magma to escape. A global increase in seismic activity would therefore likely be accompanied by a global increase in volcanic activity, adding to the atmospheric disruption through the injection of sulfur dioxide and particulates into the stratosphere. One would lead to the US common death, which would reduce solar energy reaching the surface and further disrupt agricultural systems and climate patterns. The scenario compounds on itself. Climate disruption reduces food production. Increased seismicity damages infrastructure, displaces populations and disrupts supply chains. Increased volcanism further disrupts climate. The cascading failure of interconnected systems, the agricultural system, the logistical system, the energy system, the political system, would be a civilization-scale challenge of a kind that no historical event has prepared us to address. None of this is inevitable in the sense that a gradual enough stop would allow each system to adapt. The Earth has experienced substantial changes in rotation rate over geological time. The transition from the 6-hour day of the early Earth to the current 24-hour day represents a factor of 4 reduction in rotation rate, and life not only survived, but diversified and flourished. The difference is the timescale. Over billions of years, everything adjusts. The atmosphere, the ocean, the biosphere, the magnetic field, the shape of the planet. Over decades, nothing can fully adjust except the atmosphere, and even that adjustment is catastrophically disruptive. It is worth pausing here to consider what Earth's rotation has actually given us, not in the abstract, but specifically in terms of the features of the planet that we depend on and that we sometimes take as simply how planets are, when in fact they are specifically products of this particular planet's particular rotation rate. The 24-hour day is the pacemaker of essentially all of Earth's biology. Every organism that has ever lived on Earth, with the possible exception of some deep-sea hydrothermal vent organisms, which live in perpetual darkness and may not have a circadian rhythm, has evolved in an environment structured by the 24-hour cycle of light and darkness. The circadian clock, the internal biological timekeeping mechanism found in virtually every organism from cyanobacteria to humans, is tuned to the 24-hour period. The expression of thousands of genes in human cells is controlled by the circadian clock, timed to be active at the appropriate phase of the day-night cycle. The sleep-wake cycle, the immune response, the metabolic rate, the reproductive cycle in many organisms, all of these are regulated by the circadian clock, which is kept synchronized with the environment by light. An organism evolved for a 24-hour day would be profoundly disrupted by a permanent day or a 27-day day, or any other fundamental change to the day-night cycle. Not because the organism's cells could not function, but because the temporal organization that makes the organism's physiology coherent would be lost. The biochemistry of the circadian clock is now understood in remarkable detail, and it is worth describing because it illustrates how deeply the Earth's rotation has been incorporated into the molecular machinery of life. In humans, and in most animals, the master circadian clock resides in a tiny region of the brain called the suprachiasmatic nucleus, the SCN, located in the hypothalamus, just above the optic chias, where the optic nerves cross. The SCN contains about 20,000 neurons, each of which runs its own approximately 24-hour molecular clock, and which synchronize with each other and with the external light-dark cycle through neural connections and intercellular signaling. The master clock of the SCN then coordinates the clocks of all other organs in the body through hormonal and neural signals, primarily the hormone melatonin, secreted by the pineal gland in response to SCN signals at night, and cortisol, secreted by the adrenal glands in response to SCN signals in the morning. The peripheral organs, the liver, the lungs, the heart, the immune system, all have their own clocks that are reset daily by signals from the SCN, ensuring that all the organs of the body are temporally coordinated, their physiological functions timed to occur at the appropriate phase of the day-night cycle. At the molecular level, the clock is generated by a feedback loop involving a handful of genes: clock, BMAL1, PER1, PER2, CRY1, CRY2, and a few others, whose protein products interact in a feedback loop that takes approximately 24 hours to complete one cycle. Clock and BMAL1 proteins form a complex that activates the transcription of PER and CRY genes. The PER and CRI proteins accumulate in the cell, then enter the nucleus, and inhibit the clock BMAL1 complex, shutting down their own production. As the PER and CRI proteins are slowly degraded by ubiquitin-mediated proteolysis, the inhibition lifts, clock BMAL1 becomes active again, and the cycle begins anew. The period of this loop is tuned to approximately 24 hours by the rates of protein synthesis, post-translational modification, and degradation, a remarkable example of precise biochemical timekeeping operating at the level of individual molecules. This molecular clock, operating in nearly every cell of your body, is the Earth's rotation encoded in protein interactions. It's evolved over billions of years of selection pressure from the day-night cycle, optimizing the timing of physiological processes to the most favorable phases of the light-dark environment. Animals hunt at the most energetically favorable times. Plants photosynthesize during the day and perform carbon fixation and other metabolic tasks at night. The immune system is more active at certain times of day. The vulnerability to infection varies with the circadian phase, and the severity of disease outcomes can depend on when an infection occurs relative to the circadian clock. 1.2 million, 1.3 million. The timing of cell division is regulated by the circadian clock, with DNA replication and cell division preferentially occurring at phases when UV exposure is lower, reducing the rate of UV-induced mutations. Disrupt this clock, as happens to shift workers and frequent long-distance travelers, and the consequences are well documented: increased risk of metabolic syndrome, cardiovascular disease, certain cancers, and immune dysfunction. The human cost of circadian disruption in modern society, imposed by artificial lighting and irregular schedules, is a real and quantified public health issue. Multiplied to the scale of a permanent change in the day-night cycle, an elimination of the cycle entirely, or a stretching of it to 27 days, the biological consequences would be incomparably more severe. Every organism would be running its clock in an environment completely mismatched to the clock's period, and unlike the shift worker who spends occasional nights awake but returns to a normal schedule, there would be no return to normal. The mismatch would be permanent. The clock would continue ticking at its 24-hour period in a world that no longer has a 24-hour cycle, and the biological consequences of the mismatch would compound with every generation, driving selection pressure for new clock configurations. But that selection would take millions of generations to produce a well-adapted organism, not the years or decades that would be available before other consequences of the stopped rotation made the environment uninhabitable for most surface life. The seasons, the annual cycle of temperature and day length, that drives plant growth, animal migration, and agricultural cycles are produced by the combination of Earth's rotation and its axial tilt. If Earth stopped rotating but maintained its axial tilt, the seasons would disappear in their current form. A non-rotating Earth tilted at 23.5 degrees would have a permanent summer hemisphere and a permanent winter hemisphere, with the sun tracing its highest arc in the sky over the hemisphere tilted toward it and its lowest arc over the hemisphere tilted away. The seasons as we know them, the annual oscillation of the sun's angle across the sky, the progression from long warm days to short cold days, the phenological cycles of flowering and leafing and fruiting that agriculture depends on, would cease. The agricultural systems of the world are built around these seasonal cycles. The elimination of seasons would require a complete restructuring of how food is grown, where it is grown, and what crops are viable in each location. The Coriolis effect, the apparent deflection of moving objects caused by Earth's rotation, is not just a curiosity of the atmospheric and oceanic circulation. It is the organizing principle of large-scale fluid dynamics on a rotating planet. It determines the direction that hurricanes rotate in each hemisphere, counterclockwise in the northern hemisphere, clockwise in the southern, and it is this rotation that allows hurricanes to develop the eye-wall structure that concentrates their intensity. It organizes the jet streams, the gyres, the monsoons, and the trade winds. Without the Coriolis effect, these organized, recognizable features of the global climate system would not exist in their current forms. Weather patterns would be fundamentally different in character, not just weaker or stronger versions of current patterns, but qualitatively different, organized by different principles. Predicting weather in such a world would require different models, different intuitions, different millennia of observational experience. Earth's rotation also affects the shape of the planet's day-night temperature contrast in a way that makes the climate moderate rather than extreme. A slowly rotating planet has a large temperature contrast between the sunlit and dark sides because the sunlit side has a long time to accumulate heat, while the dark side has a long time to radiate it away. A rapidly rotating planet has a smaller temperature contrast because the sunlit side doesn't accumulate as much heat before the planet rotates it away from the sun, and the dark side doesn't radiate as much before it is brought back into sunlight. Earth's current 24-hour rotation rate is in a regime where the day-night temperature contrast is modest, typically 10 to 20 degrees Celsius at most locations, and the climate is relatively uniform compared to what it would be if Earth rotated much more slowly. The moderate temperature contrast is one of the reasons liquid water can exist at most latitudes, and the climate supports such a diversity of biomes. And the magnetic field, as we discussed, is maintained by the geodynamico, which depends on the Earth's rotation. The magnetic field shields the atmosphere from erosion, deflects the most energetic cosmic rays, and provides the navigational reference that migrating animals, birds, sea turtles, salmon, certain insects use for orientation. These animals have magnetoreceptors, biological sensors for magnetic field direction, that they use in combination with other cues to navigate over vast distances. A weakening or loss of the magnetic field would disorient migratory species, disrupt the behavioral systems that have evolved over millions of years of stable magnetic field geometry, and potentially threaten the survival of species that depend on long-distance migration for access to breeding grounds, food sources, or overwintering habitat. Taken together, these dependencies, the circadian clock, the seasons, the Coriolis organized weather, the ocean gyres, the magnetic field, the moderate temperature contrast, paint a picture of an Earth whose habitability is not merely the product of its distance from the Sun, its liquid water, or its atmospheric composition. It is the product of its rotation. The rotation is woven into the fabric of the planet's systems at every level, from the molecular biology of the circadian clock to the planetary scale dynamics of the geomagnetic field. Removing the rotation does not simply change some parameters in the climate system. It removes the organizing principle from multiple interconnected planetary systems simultaneously. The cascading consequences are severe precisely because the systems are coupled. A change in atmospheric circulation affects the ocean circulation, which affects the distribution of heat, which affects the pattern of evaporation and precipitation, which affects the distribution of fresh water, which affects every ecosystem that depends on it. This interconnection is the reason that what would happen if Earth stopped rotating is not a question with a simple answer. It is a question whose answer is an entire new Earth, transformed at every level, from the planetary to the cellular, slowly or quickly, depending on how the stopping occurs, but transformed nonetheless. The Earth without its rotation is a different planet. Not Mars. It has the right distance from the Sun, the right atmospheric composition, the right liquid water, the right history of life, but a different version of itself, organized by different dynamics, supporting different ecosystems, experiencing a different climate, navigable only by a different biology that has never existed and that would take billions of years to evolve if the transition was slow enough to allow evolution to proceed. There is a deeper lesson in all of this that goes beyond the specifics of rotation and its consequences. It is a lesson about what we mean when we say a planet is habitable. We tend to list the conditions for habitability as a kind of checklist: liquid water, moderate temperatures, protection from radiation, a stable energy source. Earth checks all these boxes, and we attribute its habitability to these features. But what we have seen in this exploration is that most of these features are themselves products of a more fundamental property of the planet: the fact that it's rotating at a specific rate, in a specific direction, maintained by a specific history of angular momentum that traces back to the solar system's formation from a rotating molecular cloud 4.6 billion years ago. The liquid water on Earth's surface is partly maintained by the moderate temperature contrast enabled by the rotation rate. The protection from radiation is provided by the magnetic field generated by the geodynamo that requires the rotation. The stable, predictable seasons that allow complex ecosystems and agriculture are products of the rotation combined with the axial tilt. Remove the rotation and you remove not just one checkbox from the habitability list, but several simultaneously, because several of the checkboxes were secretly dependent on the same underlying property. This is an important lesson for the search for habitable planets beyond our solar system. When we identify a planet at the right distance from its star, in the habitable zone, we are identifying a planet where liquid water is energetically possible. But whether that planet actually has liquid water depends on a host of other factors, including its rotation rate. A planet tidally locked to its star, the default state for planets orbiting close to small, cool stars like the red dwarfs that are the most common stellar type in the galaxy, has one side permanently facing the Sun and one side permanently in darkness. Whether such a planet can maintain liquid water at the terminator in the face of the day-night temperature contrast and the atmospheric and oceanic circulation patterns that a slow or absent rotation implies is an active area of research in planetary science. The most carefully studied example is the TRAPPIST-1 system, 7 Earth-sized planets orbiting an ultra-cool red dwarf star about 39 light-years away, discovered between 2016 and 2017, and subsequently characterized in detail by Spitzer, Hubble, and the James Webb Space Telescope. 3 of the 7 planets orbit within the habitable zone. All 3 are almost certainly tidally locked to the star. Their orbital periods range from 6 to 19 days. And at these distances from a red dwarf, tidal synchronization is essentially guaranteed on astronomical timescales. The rotation of each of these planets has been erased by their star's gravity, in exactly the same way that the Moon's rotation was erased by Earth's gravity billions of years ago, locking the same face of the Moon toward us forever. Atmospheric general circulation models of tidally locked TRAPPIST-1e, in many ways the most promising candidate for habitability in the system. With a size and mass close to Earth's and an orbital period of 6.1 days, produce a picture that closely resembles what we have been describing for a stopped Earth. The day side, permanently sunlit, develops a large convective storm system over the substellar point. The night side is cold. The terminator is a zone of moderate temperature where the circulation transports heat from day to night. Whether water accumulates preferentially on the cold night side as ice, a cold trap that sequesters water and potentially collapses the atmosphere, or is maintained as liquid at the terminator, depends critically on the atmospheric pressure, composition, and heat transport efficiency. For Earth-like atmospheric pressures, the models generally suggest that a planet in TRAPPIST-1e's position could maintain liquid water at the terminator and possibly across much of the day side. But the result is sensitive to whether the planet has retained its atmosphere against the intense UV and X-ray bombardment from its active red dwarf host. The James Webb Space Telescope has begun directly observing the TRAPPIST-1 planets in thermal infrared, measuring the heat emitted from their night sides as they pass behind the star and reappear, to search for evidence of atmospheres. The first results, published in 2023 for TRAPPIST-1b, the innermost planet, found a dayside temperature higher than expected if an atmosphere were redistributing heat around the planet. This is consistent with little or no atmosphere, a bare rock heating and cooling with no atmospheric buffer. The implications for the outer, potentially habitable planets remain to be determined. They orbit farther from the star, receive less UV bombardment, and may have retained their atmospheres, but the early results remind us that being in the habitable zone is a necessary but not sufficient condition for habitability. The rotation rate matters. The atmospheric retention matters. The history of the planetary system matters. All of this research on tidally locked exoplanets is, in a very real sense, research on what a stopped Earth would look like. The physics is the same: permanent hemispheric asymmetry, a circulation driven by the day-night temperature gradient rather than by rotation, a terminator zone as the only region of moderate conditions. The TRAPPIST-1 planets are nature's laboratory for the stopped rotation scenario, scaled to somewhat different stellar and planetary parameters, but governed by the same fluid dynamics and the same thermodynamics. Every general circulation model run on a tidally locked exoplanet is, implicitly, a model of the long-term fate of a non-rotating Earth. The scientists building those models are not just trying to understand distant worlds. They are illuminating, by contrast, why the rotating Earth we actually live on works the way it does. Now consider what the stopped rotation would mean for the photosynthetic machinery of life. Photosynthesis, the conversion of sunlight and carbon dioxide into organic matter and oxygen, is the foundation of essentially every food web on the planet. It powers every plant, every herbivore, and by extension, every carnivore and omnivore. The rate and timing of photosynthesis are directly regulated by the day-night cycle. Plants are not photosynthesizing at night, they lack the light, and the biochemical machinery of photosynthesis requires photons. The Calvin cycle, the sequence of enzymatic reactions that fix carbon dioxide into sugar, shuts down in darkness and restarts at dawn. The light reactions, which split water molecules and generate the ATP and NADPH that power the Calvin cycle, require photons directly. The alternation of photosynthesis by day and respiration by night is not incidental to plant metabolism. It is the temporal structure around which plant physiology has been optimized by hundreds of millions of years of evolution. In a world where one hemisphere is permanently lit and the other permanently dark, the entire photosynthetic strategy of the world's vegetation would need to change. On the permanent day side, continuous light would mean continuous photosynthesis is theoretically possible, but most current plants are not equipped to exploit this efficiently. They have evolved regulatory mechanisms calibrated to a 24-hour cycle, photoinhibition protections that activate at midday to prevent photosystem damage, circadian regulated gene expression that prepares photosynthetic machinery for dawn, stomatal aperture cycles tied to the light-dark rhythm. Under continuous bright light, many species experience chronic photoinhibition. Their photosynthetic efficiency declines as the protective mechanisms are overwhelmed and the reaction centers are damaged by excess excitation energy. Species adapted to the current day-night cycle would initially perform poorly on the permanent light, just as a person forced to work continuously without sleep performs poorly regardless of the availability of work. On the permanent night side, no photosynthesis would be possible at all. Every plant, every phytoplankton, every photosynthetic organism in the permanent dark would die within weeks to months as they exhaust their stored energy reserves and are deprived of the light that enables replenishment. The night-side biosphere, stripped of photosynthesis, would collapse to whatever the early life of a cream, where it enables you to complex and create a fine kerosynthetic organism. Sparse community, compared to the photosynthetically fueled ecosystems currently covering the night-side's land masses and oceans. Only the terminator zone, the narrow ring of permanent twilight where the sun sits perpetually at or near the horizon, would provide stable illumination suitable for photosynthesis. The low-angle light of a permanent horizon sun is not as energetically efficient for photosynthesis as the direct overhead illumination of midday in the tropics, but it is steady and continuous, and many plant species are well adapted to low-angle, indirect light. The terminator might, over evolutionary time, develop a rich photosynthetic ecosystem, the one habitable strip of a planet otherwise divided between blazing infertile heat on one side and lightless frozen darkness on the other. Life, if it survived the transition, would concentrate there, and the agricultural consequences of this transformation would be immediate and catastrophic. Every crop system humanity has developed, rice paddies in monsoon-driven Asia, wheat fields in the temperate middle latitudes, maize cultivation in the tropics and subtropics, the complex seasonal rhythms of viticulture and orcharding across every continent, is calibrated to the 24-hour day-night cycle and to the seasonal variation produced by Earth's axial tilt and orbital motion. A fundamental disruption of the light regime, arriving far faster than any agricultural system could adapt to, would eliminate food production across most of the planet's currently cultivated land. The food security of a global civilization of 8 billion people, built on the assumption that the sun rises and sets every 24 hours, and that seasons follow their familiar annual rhythm, would collapse in months to years. Earth's current rotation rate of once per 24 hours is, in this context, neither a cosmic accident nor a physical inevitability. It is the current value of a continuously evolving parameter set by the history of the Earth-Moon system and the ongoing tidal friction that happens to place us in a regime where the planet's systems, atmospheric, oceanic, biological, geomagnetic, work together in the coherent, interconnected way that makes the planet not just habitable, but extraordinarily diverse and productive. Change that parameter, stop the rotation, or slow it dramatically, and the coherence breaks. The systems, no longer organized by the same rotation, no longer reinforced by the same Coriolis effect, no longer synchronized to the same planetary cycle, reorganize into a different pattern. The new pattern may sustain some form of life under some conditions, in some regions, but it would not be the Earth we know. It would be something new, something that the history of life on this planet has never encountered, something for which billions of years of evolution have left no preparation. We live on a spinning world. The spin is not incidental, not decorative, not a feature that could be removed without consequence while the rest of the planet continues unchanged. It is the engine. It is the clock. It is the organizer of winds and waters, the generator of the magnetic shield, the creator of the day-night rhythm that every cell in every organism on this planet is synchronized to. We carry the Earth's rotation in our biology, in the circadian clocks that govern our sleep and waking, our metabolism and immune function, our moods and our cognition. We are, in the most literal sense, spinning creatures on a spinning world, evolved by billions of years of selection to thrive in the conditions that the spin creates. It is worth pausing to consider how recent our understanding of this is, because for most of human history, the rotation of the Earth was not understood at all. The heliocentric model of the solar system, with the Earth rotating on its axis and orbiting the Sun, was proposed by Copernicus in 1543, but remained controversial for a century afterward. In the Ptolemaic model, the Earth sat motionless at the centre of the cosmos, and the apparent rotation of the stars around the celestial pole was the actual rotation of the celestial sphere. The notion that the solid ground beneath your feet was moving, rotating at more than 1,000 kilometers per hour at the equator, was deeply counterintuitive to anyone who had not thought carefully about inertia and reference frames. The definitive physical demonstration of Earth's rotation in a way that could be observed directly, without reference to astronomical observations, came in 1851, Earth overstated by Levin, when the French physicist Léon Foucault suspended a 67-kilogram iron ball on a 67-meter wire from the dome of the Panthéon in Paris and set it swinging. As the pendulum swung, its plane of oscillation appeared to rotate, clockwise, in Paris, at a rate of about 11 degrees per hour. Foucault understood that the pendulum was not actually rotating. The pendulum was maintaining its plane of oscillation in inertial space, in the reference frame of the stars, while the Earth rotated beneath it. The apparent rotation of the pendulum's plane was the Earth's rotation, made visible. At the North or South Pole, a Foucault pendulum would complete one full apparent rotation in 24 hours, exactly the sidereal day. At intermediate latitudes, the period is longer, by a factor of 1 sign latitude. In Paris, at 48.9 degrees north, the factor is approximately 10.75, giving a rotation period of about 32 hours and a rotation rate of about 11 degrees per hour. The pendulum measured the Earth's rotation from inside a building in Paris without any telescope or astronomical reference, using nothing but a weight, a wire, and careful observation. Foucault's pendulum was not just a demonstration, it was a vindication, the physical proof, after 3 centuries of argument, that the Earth was indeed spinning. You could see it happen. In an era before GPS, before satellite imaging, before any of the modern technology that makes Earth's rotation tangible and measurable to anyone with a smartphone and an internet connection, the slow rotation of a pendulum swing in a Paris dome was the most direct evidence anyone had ever presented that the ground beneath their feet was moving. People who came to watch the pendulum in 1851 left with a visceral, physical intuition about the rotation of the planet that no astronomical argument could have provided. The Earth was turning. You could watch it happen. We can still watch it happen. Foucault pendulums exist in science museums around the world. GPS satellites, corrected for the same relativistic effects that make Earth's rotation precise and quantifiable, work because the Earth's rotation is known to extraordinary accuracy. The satellites or weather agencies map the spiral structure of cyclones and anticyclones, the Coriolis-driven rotation of storm systems that is Earth's rotation made visible in water vapor and cloud. Every hurricane that spins counterclockwise in the northern hemisphere and clockwise in the southern is Earth's rotation made storm. Every compass that points north is responding to a magnetic field generated by the rotation-organized geodynamo. Every bird that navigates by the magnetic field is using Earth's rotation as its guide. The rotation is everywhere, once you know how to see it. It is in the tides and in the storms, in the ocean gyres and in the circadian clock ticking in every cell of your body, in the aurora at the poles, and in the deflection of a thrown ball, in the annual rhythm of the seasons, and in the daily rhythm of sleep and waking. It is in the fossil growth bands of a 380 million year old coral, and in the retroreflector on the moon's surface, measuring the moon's recession at 3.8 centimeters per year. It is in the planet's slightly flattened shape, and in the ocean's slightly higher equatorial level. It is in everything, because it made everything, or at least, it made everything into the form we know. Knowing that, and knowing what would happen if the spin stopped, the walls of oceans surging east, the atmosphere stripped to a planetary wind, the magnetic field slowly fading, the climate reorganizing into permanent hemispheres of light and dark, the seasons dissolving, the weather losing its familiar architecture, the deep cold of the night side settling in forever where twilight used to be. Knowing all of this does not produce fear. It produces something more useful. It produces recognition of what we have, of how specifically it was built, of how precisely calibrated the conditions are that allow us to exist in the form we do, thinking the thoughts we think, asking the questions we ask. There is a version of this realization that is merely comforting, that looks at the rotation and says, we are lucky. And that is true in its way. The rotation rate we have, the 24-hour day, the particular angular momentum that the proto-Earth happened to carry from the solar nebula, and that was modified in the right direction by the giant impact that formed the moon. These are the result of contingent history, not of necessity. A slightly different impact, a slightly different mass ratio, a slightly different initial angular momentum, and the rotation could have been faster or slower, the day longer or shorter, the tidal evolution proceeding at a different rate. We inherited this particular rotation from the chaos of the early solar system, and it has been good to us. Lucky is not too strong a word, but there is a deeper version of the realization, one that goes beyond luck. It is the recognition that the questions we ask about what would happen if Earth stopped rotating are themselves the product of the rotation. The curiosity that drives you to watch a video like this one, to wonder about the physics of a rotating planet, to think about ocean waves and magnetic fields and circadian clocks, that curiosity is the product of a brain that evolved on a rotating planet, in the rhythms of day and night, in a biosphere organized by the Coriolis effect, protected by a magnetic field generated by the rotation-organized geodynamo. The wondering is part of what the rotation made. The question is part of the answer. The Earth spins. It has always spun, since the disk of gas and dust that formed the solar system collapsed, and conservation of angular momentum spun the nascent planet like a top. It will spin for another 5 billion years, slowing imperceptibly, 1.5 milliseconds per century, as the moon pulls it gently backward through the tides. And in those 5 billion years, the spin will continue to do what it has always done: organize the air, drive the ocean, generate the field, keep the clock, and make this world exactly what it is. Not permanent, not guaranteed, just present, right now, doing its silent and essential work, the most important rotation in our solar system, the rotation that makes every sunrise not just beautiful, but necessary, not just predictable, but foundational, not just a feature of life on Earth, but one of the primary reasons there is life on Earth at all. The planet beneath you is turning at this moment. It has been turning since before the first cell divided in the first ocean. It will turn long after the last ocean evaporates. And in the thin window of time between those two events, in the geological instant that contains the entire history of life and the entire future of intelligence on this world, the turning is everything. The turning is the clock that life runs on. The turning is the engine that drives the air and the water. The turning is the shield that keeps the atmosphere in place. The turning is the reason that when you look up at the night sky and see the stars wheeling overhead, you are not simply watching them move. You are feeling the planet move beneath you, carrying you along on its ancient, patient, irreplaceable spin, a spin that began in the collapse of a molecular cloud 4.6 billion years ago, and that ends, if it ends, in a silence so complete and so alien that nothing alive on this planet today would recognize the world that followed. The spin is the story. The rest of the planet's habitability is a consequence.